All right, time for another DraftPhysics.com debate. Physics.com also. But again, the debate is non-existent in terms of all of the arguments that have been made regarding all the unevidenced claims by physics. 4 pounds dropped 1 foot is the same energy at impact as 1 pound dropped 4 feet. Never proven, never demonstrated, never shown. 25 times the fuel to go 5 times as fast, or going 5 times as fast as 25 times the impact. Not even close to a shred of evidence indicating this has anything to do with the truth. 8-pound bowling ball going 16 miles an hour somehow has twice the energy as a 16-pound ball going 8, but nobody can show it. Nobody can show it knocking down a single extra pin or anything like that. Can't show any of this kinetic energy to have any reality whatsoever. Ballistic pendulum, you try to collect the momentum of the bullet. It has 2,000 joules of energy. What comes out? 1.4 joules. Yeah. 0.06%. Pathetic. Okay, yeah, right. Just no evidence. Okay, and they don't care. They just don't care. You just keep preaching the dogma. They don't care. They can't respond, and they won't respond, and they'll just preach dogma. And that's the reality. They'll call you an idiot and a science denier because you merely say, show me. It's not acceptable for somebody in the science community to say, show me. No. We have to just believe them. Okay? And that's it. They're the authorities. Yeah. No, it's just bullshit. And it's sad and tragic bullshit. I mean, frankly, if you're watching physics videos, I would assume you are somebody who has spent their life saying, I'm going to observe, I'm going to collect information, I'm not going to be an idiot, okay? And you're behaving like idiots. Because I'm not challenging with anything too abstract. The simple argument that they've never tested any of this stuff, you should be able to concede, yes, they should test it. They should do the Eddington experiment from space. They should do these things. And to deny that it's wrong that they haven't is just demonstrating that you're not about the science. You're not about defending the idea of science. You're just about dogma and preaching. It's pathetic. So anyway, so Professor Dave does the standard, let's do the 3 laws of motion, and he gives them all really short shrift. And obviously in the second law he just makes up crap that ain't true. Newton never said, and it's a standard bullshit. So we'll play through them. I wrote the little spiel there. That really you could reduce Newton's 3 laws into one law of conservation, because they're all basically saying that, what goes in, the same thing has to come out. It's just about following the motion, and that's all there is. There's a certain amount of motion in the universe in terms of the number of little discrete bits, electrons and protons moving, and if you just watch where the energy goes in terms of where the electron's moving. So you can have a whole bunch of electrons in a big object moving slow, or you can have 3 or 4 electrons moving fast. Same thing. Same energy. Okay. Because they have to collect them to move fast. To move fast, the 4 electrons have to have 100 electrons each. The 400 only have to have 1 piece of force pushing them each. But it still adds up to the same thing, 400 units of force. And, it's that simple. And they've turned it into garbage.
He knows a lot about the science stuff, Professor Dave explains.
Jerk.
In Newton's Principia, he describes...
So again, you have to argue, who are these videos for? You kind of think they're supposed to be for college students or high school students or something, but I mean, it's just, they're all over the place. Complex abstract crap, and then this kind of, we don't even know who Newton is. So who doesn't know who Newton is? A 10-year-old? I mean, who are you talking to?
3 laws of motion, and the first of these 3 was revolutionary. It can be summarized as follows.
It's just bizarre that you would call the first one revolutionary when it's saying the most obvious thing, in a sense. And obviously, even in Newton's time, they knew what friction was, so it wasn't a surprise that, okay, yes, if there was no friction, what would happen? Is that a really complicated thing to ask? I don't think so. Yeah, I don't think so. I mean, to understand that they already understood the atmosphere as essentially being very thin water, that the atmosphere is a substance, okay, that we're moving around in, and that if you took that substance away, well, then there's not going to be this obstacle that we have to push around, yes, it'll make things a lot easier to keep your energy if you don't have atmosphere rubbing against you and stealing it all the time. So it wasn't that revolutionary a concept.
An object at rest will remain at rest, and an object in motion will remain in motion, unless acted upon by some external force.
Yeah, and again, the idea of external just means as long as it's not a piece of dynamite or something. I mean, it's just like as long as it's not going to spontaneously explode. The only thing that's acting are these features of the environment. And clearly it's not about being acted upon by another force. You're just interacting with other matter. And you're going to have to share your force with the matter you're interacting with. And that's the obligation. So friction isn't a force. I mean, friction is just you making contact with some other matter that has to take your energy. You're going to have a conflict with the other matter. You're going to hit it. You're going to interact with it. And as soon as you interact with it, you're going to share your condition. And if it, relative to you, okay, isn't moving, then you're going to end up causing it to move. And you're going to lose your movement because you have to give it to the other object. So it's essentially just giving away the force. The force has to be conserved. The units of pushing energy in the universe has to be conserved. And so if you make it move, you have to move less.
The first part seems to make sense, since motionless objects typically don't just start moving. But the second part contradicts.
I mean, it's not just typically, it's like universally just don't start moving. And again, unless they're a stick of dynamite or something, have some sort of mechanism that has obviously a time bomb in it of some kind that's going to make it blow up. And clearly nothing ever spontaneously does anything.
Much of our everyday experience. When you throw a ball, it doesn't keep moving forever. It eventually stops.
Yeah, but the rule there is there's two stupid forces, right? There's the stupid air that's making a mess, and then you have gravity pushing it into the ground. So you have to throw it fast enough to put it in orbit. If there was no atmosphere, it's still going to hit the ground because you're going to have to throw it at like 1,000 miles an hour. You're not going to be able to do that.
For a wheelbarrow to roll, or for your car to move, or for a plane to stay in the air, a constant force must be applied.
So it doesn't have to be constant. It can be increasing, decreasing, it can be doing all kinds of stuff. So again, that's not even accurate. All right, you just have to maintain more force than you're losing to friction. There's another video I wanted to do with the Alpha Phoenix guy, because he touched upon Tesla's idea of resident additions of energy, and it's just that it's that simple. I mean, if you're losing energy, then your system has to be pushing more energy in than you're losing, or your system will lose energy. So you have to keep putting more in if you're losing more out, and the faster you're going, the more you're going to lose out, and then you end up with a terminal velocity, because the force of gravity in can only produce so much motion out. And if you're losing it, more than or equal to, then you stop gaining any acceleration. You just keep going the same speed.
So where did Newton come up with this stuff? To understand...
So he came up with it just by visualizing what it would be like if there wasn't this fluid that we're moving through. Obviously, you could see the difference between how slow something is. Really hard throwing a baseball underwater. And you could think, okay, it's easier in atmosphere. Well, it's going to be even easier without the atmosphere, obviously. And obviously, every one of us calculations regarding the moon's orbit and everything else, there's no friction. So obviously those had already given him an indication that out there's no atmosphere getting in the way, stealing, retarding. No, stealing's a better word. Rubbing up against something, interacting with something to take its energy. There's no interactors out there in space.
Newton's first law of motion, we have to understand all of the forces that act on a body in motion.
No interaction that could matter, in the sense that if you have something going, a force moving the speed of light, moving in both directions, and then you're moving 10 miles an hour, the drag force is going to be almost irrelevant because both forces are moving so much faster than you are that there'd be an insignificant differential in how much you're going to be affected by the forces. So you have to move very fast to start experiencing anything like drag.
Our planet is a complicated system, and when we move around in our atmosphere,
So we know that it's not that complicated if you're looking for just drag mechanisms or rubbing mechanisms or friction mechanisms. They're really simple. So it's just atmosphere, and then there's denser liquids, and then there's solids. And obviously you can't throw the baseball inside the solid.
we experience things like wind resistance and other forms of friction.
So, he shouldn't have called it wind resistance. He just should have called it atmospheric or air pressure, air molecules.
Which is a force that resists motion.
So again, it doesn't resist motion, it takes motion. It hits you. The molecules hit you and they take away your velocity. They bounce off at more velocity. So you throw a tennis ball at a car coming towards you. The tennis ball comes back at you with more velocity than you threw it, because the tennis ball just took a little tiny bit of the car's velocity. That's all it did. It stole some of the car's energy and bounced off with that extra momentum. And that's happening constantly in the atmosphere. The atmosphere is constantly, if you move this way into the atmosphere, the air molecules you hit going that way leave with a little bit more energy. And they took the energy from you.
This is what slows us down, requiring the application of constant force to keep moving. But think of something like
And the irony is that it's not really the drag forces forward, because you're escaping forces in the reverse. It's the side ones and stuff. So it's things like turbulence and whatnot are where the stuff is spinning around and doing other things. It's all motion. And all that motion has to come from the original moving object.
skating rink.
I mean, all of the, waves coming off the wake of a boat, all of that movement is retarding the motion of the boat. That's all waste.
The ice is very slippery. It is a surface with very little friction. If you gently push a hockey puck, it will glide rather far, much farther than if you pushed it on a table or on the...
Yeah, but it really depends on the conditions, right? Because as soon as the ice gets a little sloppy with some water, then all of a sudden the puck starts sticking because of the adhesion of the water on the ice.
ground. But there is still some friction, so it eventually does stop. Now imagine, as Galileo and Newton did, that there is a surface that is completely free of friction. If you push the...
I don't think they did it by thinking of surfaces free of friction. I think they did it thinking of cannonballs free of air. But whatever.
hockey puck on this surface, whatever velocity it has when it leaves the stick, would be retained indefinitely, and it would glide forever, unless some other force were to act upon it.
So even that forever stuff is sort of bogus, because we know space does have some atoms in it, hydrogen. You're going to have to hit them. You're going to lose a little bit of energy, and so it's not forever motion.
This is the kind of motion that can be seen in the vacuum of space. Stars and planets and asteroids and satellites, these objects have roughly constant velocity, and they never stop moving.
So their velocity is clearly not constant because they're all not in perfect circle orbits, and so their velocity is constantly changing, going very fast, when they're very close, going very slow when they're very far away, blah, 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 blah. So he didn't even get that quite right. So there is no constant velocity. There's a constant, you could argue, equalization to the force, okay, the gravity force. So yes, when they're in strong gravity, they gain velocity. When they're in weaker gravity, they lose velocity.
As it happens, most of the universe is in space, and very little of it is on Earth. So we should consider motion in space where there is no friction and no...
All right, so we know there is friction in the sense that we know there are gravitational objects, and all of those, in a sense, are kind of, they're going to change our capacity to move forward if you're fighting a gravitational field. So that's a kind of friction. It's a real force this time. It's not exchanging, okay? It's the fact that there's a real force pushing you in the opposite direction. But it's the only case where it's a, real force rather than just an exchange of force.
No wind resistance to be normal motion. It is motion within Earth's atmosphere that is the special case, where objects are subjected to a variety of variables.
So again, it's not that special, and you could argue that the corona of the sun is like an atmosphere. So you could go, millions of miles from the sun, and you're still now going through a bunch of particles that you're going to have to share your energy with. Just a fact.
This is why a car needs an engine that is always running, because there is resistance.
This is just, again, I can't even imagine exactly who this is for, this video. You have to explain that a car needs an engine. Gee, but it's only a 4-minute video, and he's wasting time. It has to have round wheels, and come on.
From the atmosphere and friction with the road. But a spaceship can just accelerate to a certain velocity and then turn the engine off, and it will cruise at that final velocity without end.
So again, he said without end, but it's theoretically impossible that that could be true because it is going to hit particles and it is going to lose velocity to those particles. Fact.
The capacity of an object to resist changes in motion is...
So again, it's not any resistance. It's just saying you have to give somebody money for them to have money. So it's just that simple. So everything's poor. It doesn't have any money, let's just say. It's sitting there, doesn't have money. Is it resisting? Is it saying, don't give me no money? I refuse to take your money. No. It's saying you just have to give it to me and I'll have it, okay? So give me $10, I'll spread it over my mass, and I'll go, if I have 10 units of mass, well then, yes, each unit just gets $1. Well, velocity. I have to spread it across my mass. But you have to give it to me, or I ain't going anywhere. And then the real trick is that everything is sort of built in. It has an elasticity. So even a piece is, there's this almost, don't think you could describe an atomic structure that doesn't have some elasticity in it. That is, you can push on one electron. And if you push on that one electron, the odds are the electron just bounces back to its original position. Because unless you push it really hard, knock it out of the atom, and then cause a cascade of other problems, it just refixes back to where it wants to be. You just jiggled it, and it just jiggles back into its position again. And so you don't change the motion of the object. And the only way you can change the motion of the object is you have to get all the atoms to move. All the electrons have to move. And so obviously you can introduce energy, and the energy just reflects. And then you can introduce energy where the energy is absorbed, and it actually stays in the object you gave it to. It moves all the atoms. So the energy doesn't bounce off the surface. Key difference. Reflection and absorption are key concepts here, because you're not going to change something's motion if your force bounces off of the object.
called its inertia. Force must be applied to get an object moving. And again,
So again, if I glued that ball to the ground and it won't move, then what happens is the hammer hits the ball, it tries to move some electrons, the electrons say the ball can't move, and it just pushes them back again. The pressure you're creating, you're pushing on the earth pushes back. I mean, it just ends up creating an elastic reaction, and you end up getting the club back in your face. That's the reality.
to slow it down to a stop. Only motion with constant velocity.
So again, it doesn't have to be constant velocity. It can be increasing velocity. So you're failing. It can decrease and increase, and decrease and increase. And as long as it stays, as long as its net velocity is higher than the frictional force, it'll keep going.
Including zero velocity, requires no application of force. An object will have some amount of inertia that is proportional to its mass.
So there's no inertia, okay? There's just mass. So if, and this is just a spreading butter on bread kind of argument or something, the more mass you have, the more surface you have to cover. And so your velocity could be considered whatever it is you're spreading on the bread. And you have to have enough force to spread on an awful lot of bread. So the more mass, the more bread. The thinner the amount of stuff you've put on that bread, the slower your velocity. The thicker it is, the faster your velocity. So the less bread and the more butter, the faster the object goes.
A scalar value measured in kilograms.
So a nonsense notion of some scalar value versus some vector value, which obviously they're all scalars, end up being vectors. There's no such thing as a scalar value. There's no such thing as a motion in the universe that isn't just like that little stuff up there moving in straight lines. That's the only form the elemental force comes in, is something that moves through the universe in a dead straight line.
More massive objects have greater inertia, or greater resistance to motion.
So there's no resistance, there's just your obligation to provide enough energy that it can spread it over the whole surface, and if it can't spread it, then it just throws it back in your face.
Think of a tiny sailboat versus a huge luxury cruise ship. A strong gust of wind is enough to get the sailboat going.
Unless it doesn't have a very big sail. So again, this is just, there's no logic to this. He's using something with motors versus something that's catching wind, and it's all about the size of the sail. So I could put a little sail on a big boat or a big sail on a small boat. Yeah, and I'll get very different results, very different momentums.
And if it hits a rock, it will stop on impact. But the cruise ship needs huge engines to accelerate from rest. A lot of force is needed to get it going, and a lot of force is needed to get it to stop.
So it's not about a lot of force is needed to stop it. It's that you have to dissipate a bunch of force to stop it. You have to collect it. You have to take it away from it. And if you take it away really quickly, okay, yeah, it's going to make a mess. And if you take it away really slowly, there's no problem at all. So you could have a bunch of jellyfish stick to it, and take away the energy each little piece at a time, and no problem. Or yes, you could crash into a rock or an iceberg and tear the thing to pieces. So what? I mean, so obvious.
Similarly, it is easy to set a ping pong ball in motion. Just give it a flick. But a bowling ball will need quite a bit more force.
Right, so this is the joke, right? Okay, so he doesn't get to the real point, which is their second law and then 1/2 mv squared. And so here's the example again. They're using the bowling ball example. Their theory says the 8-pound ball going 16 has twice the energy of the 16-pound ball going 8. Now, there's no theoretical way to draw that. If you sat there and drew it out and tried to explain exactly how each pin flew away, and somehow each pin, when I total it up, that somehow there's twice the momentum in the pins, there won't be. All the balls can do is transfer their momentum. They can't transfer the kinetic energy. It doesn't happen. So what's the point of talking about kinetic energy as it means something when it can't do simple things like knocking pins down? The fact is it can't do it. It can't knock more pins down. It can't create anything more than exactly the same momentum transfer. So all it's going to do is transfer exactly the same momentum. Both balls will transfer exactly the same momentum. There will not be any twice anything.
And more force to stop as well, as any bowling pin will tell you. In this way,
So again, you talk about he knows what bowling pins know. I'm telling you, okay, it's just a fact. Nobody's going to draw it out and show you how the kinetic energy will be conserved, because it won't.
mass is essentially a quantitative measure of an object's inertia.
So again, it's just this. You got it backwards. Inertia is just a silly word describing the fact that you have to pour fluid into a bottle for the bottle to have fluid in it.
As we said, this applies to objects that are already in motion as well. If you get into a car accident, the force of impact will stop the car, but your inertia dictates that your body will.
So again, this is more kind of bullshit just because, well, the stuff not attached to the car, so the car stopping, the stuff that's obviously not attached to the car, okay, doesn't have to stop, right? So unless there is something sticking out of the steering wheel that pushes you into the seat and keeps you from moving, well, then you're still able to keep moving because you don't know the car stopped. I mean, there's nothing telling you except maybe your feet, but everything else is completely unaware that the car stopped. Duh. I mean, this is such a, they wasted, somebody wasted time with this kind of tacky animation.
Tend to continue moving. And this is why we wear seat belts.
Oh, so always wear your seatbelt. So this is what we get from scientists. They have to give us their little advice. Do you always eat your vegetables? Yeah.
Because without them, we might continue moving right through the windshield, which wouldn't be very fun.
Wow, yes, nobody's heard about that. Nobody knows it wouldn't be funny. Obviously, there's lots of people who think it would be funny. I mean, there's probably all kinds of fail videos online where you can watch people do this shit.
So Newton's first law can be summarized as the law of inertia.
So it's just silly. There's no need for this extra word. It doesn't mean anything, okay? It's just the fact that if you want there to be water in a bucket, you have to pour water into the bucket. If something's going to have a velocity, something has to give it the velocity. It has to take the motion, the movement from something. So either a force going the speed of light has to hit it, or something that carries the force has to hit it. But that's it.
Its state of motion, whether at rest or moving with constant velocity.
So again, with a velocity that maintains an average velocity, so it's just an average velocity that's the same as what you're losing.
We must understand what net force means, because there will often be multiple forces operating on an object. And the sum of the vector...
Right, so they don't know what net force means, and they completely misuse it in the second law example when they claim that Newton was talking about a net force when he wasn't talking about a net force. He was talking about a ratio of, here's your timed ratio, 9.8 meters per 1 second. That's not a net force, okay? That's an explicit statement about how much force you're going to get per second. It's not anything net.
Representing these forces is called the net force. If the net force is not...
So obviously friction isn't a net force. Interaction has the implication that you could draw it as a net force, but it's not a net force. So I'm just saying it's really wrong to say it's a force when, no, it's you giving away your force. It's not some counter force. You giving away $10, all right, it's not two interactions. You just gave away $10. That means you gave something $10. It has $10. You now lost $10. It's only one action. There's no opposing actions.
Zero, there will be some acceleration. If the net force is zero, there will be no acceleration. Now we can move on to the second law of motion, But first, let's check comprehension.
Yeah, that's not. Comprehension of what? I mean, this was such a silly video. The force must be applied to initiate motion in an object in, yeah, all of the above. That's right. You have to apply a force no matter where you are, or it's not going to move. Oh, duh. Oh, I hate this planet. All right, let's go find the second law, and we'll do that. All right, second law. So I think just to point out. So the idea is there's this conservation of motion in the universe, and that just means the total mass is always moving exactly the same amount. So if you do the MV thing of the whole universe, it's always the same. So the idea is that the force, the little bits, are actually little masses, very small. Okay, quantized. Okay. And it hits something. Well, the little force bit's going the speed of light. It hits something, so 3 million miles an hour. It hits something with 3 million electrons, you could argue. And so it's going to have to spread that speed, that mass and momentum over that entire object. And so, yes, it goes in. A little tiny mass goes in very fast. This big mass absorbs that tiny mass, so its mass goes from 10 pounds to 10.00003 pounds. So it gains a tiny bit of mass, but it gains a huge amount of velocity to spread over that whole giant mass. So that's the real trick, is that the speed of light hits an electron, okay, and it makes the electron go 10% of the speed of light, because let's say the electron weighs 10 times as much, that kind of thing. So you're really just combining the force mass with the object's mass and then keeping, okay, the velocity spread over that much mass. So you're always conserving, so there's always exactly the same MV, total MV in the universe, as long as you consider the force to have some kind of finite, very small mass. Which I think is obviously the truth. The force is capable of transferring momentum. It has momentum. It gives things momentum. And that's what Newton said in the second law, so I should just point that out. Newton didn't say F equals ma. Newton said the force, you want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force. Clearly saying the force is essentially momentum. It'll do exactly the same thing as a blob of momentum. So if I just take a blob of momentum, or I take a blob of force and I interact it with you, it'll do exactly the same thing. It's just going to transfer momentum, and it's purely proportional. More momentum, more momentum. That's simple. You just merely, if you're going to absorb the force, you're going to absorb its momentum. That's all. And yeah, so there's no reason to square anything. And so in Newton's formula, it says F equals a change in your momentum over the change in time, which clearly isn't a net force equation. Okay, the net force would be, who cares about the time, because the time's irrelevant. We just want to know what the net effect is. And obviously the net effect would just be 1 unit of time. Doesn't matter what the unit is, an hour, a month, a year. It's the net force. It's over the entire period. So you just kill the bottom of the fraction, and clearly the equation really is force equals the change in your momentum. And that's what he said. I mean, that's what twice the speed, twice the force means, and 3 times the speed, 3 times the force means. It means the force equals momentum. And all you're doing is transferring it from being a force, a free force, to being a force stuck inside of an object. And it's clearly just, if the force goes into the object has exactly the momentum the force had. Force is momentum. Force is weight. Force is energy. It's all the same thing. Shit. Anyway, it's just, I hate this planet. Really do hate it.
Newton's second law.
He knows a lot about the science stuff. Professor Dave explains.
probably could turn the volume down. It always ends up being a little high. Maybe I'll do it down here. That might work better. It ends up talking too loud. Singing too loud.
We learned about Newton's first law of motion, which tells us that an object will continue its state of motion unless acted upon by some net force.
Right, so he's going to waste our time, okay, doing the second law by doing the first law again.
The second law continues from there, describing what will happen if some net force is indeed present, whether from internal or external forces.
And the simple point is what Newton simply said is that the force equals momentum. That's it. So calculate the momentum of the force, and if it's absorbed, that's what you're going to get.
This law tells us that force is equal to mass times acceleration.
So it's mass times velocity because it's just momentum. Whatever the momentum of the force is, that's what you're going to acquire.
This is summarized in the following equation, F equals ma. What it means is that we can do quantitative calculations relating the magnitude of a force.
All right, so it's not Newton's formula. It's not what Newton said, okay? And it's certainly not Newton's description of this A thing as some squared commodity. That's not Newton.
Applied to an object, the mass of the object, and the magnitude of the acceleration that object will experience. And it shows the derivation of the Newton as the SI unit of force.
Right, well, they're nonsense. So again, in Newton's understanding, none of this crap is true. This isn't how he understood the force. He understood it as a weight, a pressure. So if he was to describe a Newton, he would describe it as it actually is, which is 100 grams of pressure. That's it. It's 100 grams in gravity. And 100 grams in gravity is 100 grams moving 1 mile an hour. It's the same thing. If I move up 100 grams 1 mile an hour and crash it into a scale horizontally, it compresses the scale exactly the same amount as the scale compresses when the 100 grams is in gravity. So 1 mile an hour is the speed you need to travel for your mass to be your weight. For your weight to be your mass. Let's just put it that way. So it's that simple. So the F is just 100 grams in this case for 1 Newton.
When we plug in 1 kilogram and 1 meter per second squared for mass and acceleration. There are a number of things we can...
So in some sense it could just be argued that, okay, 1 Newton, then 1 joule is 10 newtons.
...say about this equation, which is tiny but powerful.
So again, it's nonsense and garbage and a slander against Newton. So they, again, they're not standing on the shoulders of giants, they're kicking them in the nuts. It's that simple. Newton, when you appreciate you rephrasing his laws and turning them into garbage, turning them into especially Leibniz's laws. So you're basically finding some mathematical mechanism to force Newton's mechanics into turning it into Huygens and Leibniz's mechanics, and then still say it's Newton when it's not Newton. So you're just slandering one of the greatest scientists in human history, because you just don't give a fuck about the truth, and you don't have any integrity, and you're just not honest people.
First, it means that heavier objects will require the application of greater force.
Yeah, we already know that. We already knew that from the first law. So yeah, nothing new there. Obviously, more matter to push, more force energy needed. Okay, not complicated at all.
In order to achieve the same
So
acceleration...
obviously when they're falling in gravity, the hammer collects more energy. It just has a bigger sail. It has more little elements of these universal units, more universal units, electrons and protons. So obviously when it hits the ground, it's got a whole bunch of little units that collected forces, a whole bunch of little sails that got pushed on. And the feather, man, it doesn't have too many. So yeah, it doesn't hit the ground with much impact because it hasn't collected much. It's that simple. You're collecting rain in a bucket. If you're a feather, you have a little tiny bucket. If you're a hammer, you have a big giant bucket. And we just watch the rain collect in the bucket, and all we're going to measure is when you hit the ground, how much water is in the bucket. We'll tell you how big a impact there is.
As lighter objects, with acceleration being equal to force divided by mass. If we want these objects of varying masses each to accelerate at 1 meter per second squared,
So again, per second squared, whatever that means. What the hell does that mean? We don't need that. 1 meter per second tells you all you need to know. 1 meter per 1 second. So if it's 2 seconds, then it's 2 meters. If it's 4 seconds, it's 4 meters. I don't need any seconds squared. What is that for? It's a useless notation that just creates the opportunity for shenanigans. How would the physics be non-understandable if they took the square off? Oh, that's right. It wouldn't be non-understandable. It would be exactly how Newton would have wrote it. 9.8 meters per 1 second.
These are the magnitudes of the forces that must be applied in order for the math to work out. This also means...
So to say the forces that have to be applied, it's more about the forces that can be collected. So obviously the very light object can't collect the force because it doesn't have enough electrons and protons. It collects less force because it has less collectors. Obviously.
Means that the second law can be rephrased to state that the acceleration an object experiences will be directly proportional to the force applied.
So again, the acceleration, if understood as just being a unit of acceleration. So this idea that somehow you're always talking about being in gravity. Well, the point is gravity will give you acceleration, but it's a time-dependent unit. It's 9.8 meters per 1 second. If you fall for 2 seconds, you get 2 units. You don't get 4 units of anything. So again, they broke it entirely. They think because you fell 4 times the distance, you got 4 times the energy. No evidence that's true, and there's all kinds of evidence saying it's not true. Because when you fall 3, times the 3, when you fall 9 times the distance, you only have 3 units of velocity. You've only been in 3 seconds worth of gravity. You've only collected 3 units of force. That's all you have is 3 units of force. There's no other way to look at it. And as Newton pointed out, 3 units of force, 3 units of velocity. That's it. There's no 9 units of energy.
And inversely proportional to its mass. It is important to note that...
So he's doing the same damn thing. So this is the same bullet, it might as well be the same fucking clip. What's the point of this?
The net force is the sum of all the forces acting on an object.
Right, and 9.8 meters per second is not a net definition of force, okay? It's just not. It's a ratio telling you the rate. It's not telling you how many seconds it was. It's telling you how much you get in 1 second. It's just such bullshit.
If multiple forces are acting on an object, which is often the case, we will need to represent them all in a free body diagram.
So exactly the same bullshit. Yes. But exactly, if you think there are counter forces when you're giving your money away, if you think there's some counter force that took your money away. So I gave somebody $10 and I think there's a counter force that took $10 from me? No, there's no counter force that took $10 from me. I gave the $10 away. I don't have it anymore.
And then add up all the vectors to find the net force, which will tell us the direction of the acceleration that will occur in response to the net force.
And you have to get this stuff right. So if you think the net force, if you think the frictional force is the same no matter what speed you're traveling, well, you're not going to get a right answer because it isn't the same regardless of speed. Velocity.
This kind of vector addition allows us to make predictions.
And again, predictions you never test with actual experiments. So what's the point? So you're predicting that 4 pounds dropped 1 foot is the same amount of impact, same energy as 1 pound dropped 4 feet. That's your prediction. Where do you have evidence it's true? Oh, that's right. Nowhere. Never tested. in 350 years of you claiming it to be true, never tested.
About the motion of an object, even when it is being pushed or pulled in a variety of ways. Since forces are vectors,
So let's just understand again, friction is not a force, it's just contact. And every time there's contact, there's potential for an exchange. And that's all that takes place. You exchange your condition. And if you have more money than the other guy, it's likely that you're going to have less money and he's going to have more money after you're done exchanging.
they can be split up into x and y components, which will be useful for doing calculations in certain scenarios that we will investigate later.
Yes, well, and if you do those calculations in kind of the relativity context, you'll find out that, oh yeah, you can't give a photon two momentums because that means you'd increase its velocity. So photons can't go this way and go that way. You can't do both. Can't happen. Can't bend a photon.
Newton's second law of motion has an incredible range of applications.
You're right, and they're all based on Leibnizian nonsense. So the range of applications is the fake notion that there's something called kinetic energy, that it's somehow calculated by 1/2 mv squared, that somehow you quadratically increase the amount of energy you have by just increasing your velocity. So every unit of velocity you increase, you get a quadratic increase in your amount of energy by some magical mechanism, and absolutely zero physical evidence that it happens. The ballistic pendulum proves the point. 2,000 joules goes in, they collect 0.06%. They collect a percentage, they collect most of the momentum, and they lose 99.94% of the kinetic energy. Fact.
As it can be applied to any force that exists, and it describes the motion of all accelerating objects in the universe.
No, it doesn't. So it's again, if F equals ma is perverted into 1/2 mv squared, which it is, it doesn't get right answers and it won't land you on the moon. Momentum landed mankind on the moon. Understanding the exchanges through exchanges of mass and velocity, throwing things out of your spaceship that have mass and velocity. That moves the spaceship, not kinetic energy.
We can even use it to do things like calculate the masses of faraway celestial objects.
And probably doing it wrong. Okay, that's that simple. Obviously, they've done it to calculate the mass of the electron, and that's why your electrons and protons don't equal your weight, is because they got the calculation way wrong, because they use this silly, stupid, idiotic, wrong equation. Just a fact. That's how they measured the weight of an electron, is they applied 1/2 mv squared to its velocity, so its velocity was hugely important and its mass was irrelevant. And its mass would have been so much more relevant if its mass didn't have that squared velocity. So then the mass would have to make up the extra energy. Then the mass would have to be gigantic, because you weren't squaring the preposterously high velocity.
But for right now, we will just stick to the basics. So let's check comprehension.
Yeah, fuck you again. If you push a cart across a frictionless surface, so you apply 20 newtons of force for a period of 3 seconds, so it's 20 newtons times 3. They're done. Alright, anyway, just forget it. No, yes, we're not going to do any of that bullshit. Alright, so I'll pause and we'll do there's a couple of moronic comments, so I might as well do them. But I mean, they're just moronic. They just will not answer the challenge. All you have to do is show me some kind of reasonable evidence that there's some hope that it's true, that it takes 25 times the fuel to spin something 5 times as fast. And that if I spin something 5 times as fast, that it can do 25 times the work. You just have to show me some kind of evidence that that's a possible truth. And you won't do it, because it's not a possible truth, because it's absolute nonsense, and the fact that you are belligerently denying that fact makes you fucktarded, evil pieces of garbage. You're not defending science. You're not defending the truth. You're not defending human integrity. You're not defending any kind of decency or cordiality or anything. You're a scumbag. Because it's not too high a bar I'm asking you to jump over. Show me, fucker. Alright, so only a couple of dumbass comments. So this asshole says, experiment demonstrates relativity. Says you. Okay, the fact that there's what's demonstrated is that there's a thing called an atomic clock, and that the atomic clock counts seconds differently in different environments. So yeah, there might be a catch that you can break the clock by moving it really fast. That somehow that can change decay. Now we already know you can change decay by heating radioactive materials, so that's an argument right there. And all I have to do is put them next to each other, and they decay faster. So I can concentrate them, and they'll decay faster. Lots of things will cause them to decay faster or slower, and so the argument is that somehow velocity causes them to decay slower. So maybe decay has something to do with coincidentally simultaneous events taking place, or something like that, and you're disturbing the simultaneous possibility by creating velocity. Let's just make an argument that helium nucleuses have a shape like a diamond, and the fact is if they're moving in a direction, what happens is there's less energy pushing on the sides, so their sides expand, so they contract forward to back. So the faster they're going, the more they contract, the more this side expands out because there's less pressure pushing in from the sides. These are real arguments to make. Okay, you're going to pretend that because they told you so. So just like the universe is expanding because there's an expansion of the frequency of light over distance. Well, and there's no possibility, there's just absolutely no possibility that could be explained by the fact that over great distances there's every probability that photons hit hydrogen atoms. And that every time they hit a hydrogen atom, it's actually proven fact. Okay, you want to talk about experiments that prove something. That's already proven, okay, that every time you interact a photon with, say, a hydrogen atom, it will lose a little bit of its frequency through scatter. So that's already a proven fact, too. You don't care. You're just such assholes. So telling me it's demonstrated something, no, that's like saying the two-slit demonstrates photons are a wave, when no, it doesn't. If you actually look at the experiment and pay any attention to the fact that, there is absolutely no similarity between water in the case of a single slit. In the case of a single slit, water creates zero interference, and obviously in the single slit in photons, there's a ton of interference. So clearly this is about the surfaces. This isn't about making waves. So publish a paper of your own, you disingenuous hack. So again, yes, and submit it to who? I have already, look, 10 years ago I published, I submitted a paper just pointing out these simple arguments, blah, 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 and they won't even review it. So fuck it. Don't tell me, go to the Pope and convince him that we evolved on Earth and there was no need for a God. Okay. Yeah, fuck you. Just such bullshit. Alright, then this elephant. So this is a guy who has an icon of an elephant sucking its own penis. Okay, so a classy fellow. This is amazing. You want to debate physics, but you are unable to understand even high school level physics. So no counter argument to a single argument made in the video. Frankly, one of my best videos. No, just a fact. It's one of, I go through all of these issues, all of these points, nailed it in the sense of pointing out all of the fallacies. And there's no counter argument here. Like that push example that you gave with people on skateboards. Yeah, so go ahead, show me the counter evidence. Show me where they actually did the experiment, where You use the same force and you push against a brick wall and you see how fast you go on your skateboard. And then you push on another person on a skateboard. You, just your force. They don't do anything except move away from you when you push. And see what velocity you have. Have they done the experiment, you weasel? Can you show me an example of how, yeah, it doesn't matter whether I'm pushing against a brick wall or I'm pushing against a moving object, I keep the same exact energy? Oh, obviously I don't. Stupid little weasel. Let's see. It takes more than one stupid... It takes more than mere stupidity to get things so wrong. So how did I get anything wrong? Is there any argument about how I got it wrong? No. Is there any evidence I got anything wrong? No. So you're just a liar and a piece of shit. Again, is that the scientific process? You just say, I know it's true. I don't have to prove anything to you. I don't have to show you an experiment where they did this and demonstrated it. No. Again, I bounce a ball bearing on top of an anvil and it bounces 200 times and I put fucking goddamn, let's say at least 20 times the energy into the anvil and move the earth. Have you shown us the earth moving? No, you haven't. 20 times as much as the momentum of the ball. I put 20 times the momentum into the anvil. That makes sense to you, you fucking idiot? Let's see. Or the thing with mv squared. I don't even know what to say. All the best. Yeah, well, fuck you. I don't give you all the best, you fucking creep. I mean, it's really creepy, frankly, to do this little cartoon icon on the internet. You know, it's, yeah, fuck you. It's just rude behavior, frankly. Ugh, god damn, assholes. Steve-O. So this is like some character from the past. So he's asking about the modern mystic. I mean, just you can't even look him up, huh? You can't even bother doing anything yourself, huh? Oh, fucking goddamn. Let's see. The guy that does these courses aims for undergraduate engineering, math, chemistry, and physics. So who cares what he's aiming at? I'm just saying the videos are all over the place. He talks to you like you don't know what a cardboard box is 1 minute. And the next minute, he's talking this abstract, wee poofer physics. He does a solid job for this. I just point out how it's not solid at all. He just explained a magnet in the most idiotic way possible. He's talking about, well, look, these little arrows are pushing this way, and the arrows on the other one, they're pushing this way. The arrow, and you know, there's arrows pushing arrows and things, and that's how magnets work. He did this. I just did a reasonable paraphrase of his goddamn video. You fuck. Did that explain how a magnet works? You fuck! No, it didn't. Okay, it's a level of an undergraduate engineer. You keep saying the same thing like this means something to me. No, it's the level of a fucking goddamn idiot savant or an autistic kook. I mean, come on. You should not be trashing him because everything he says is true for that level. Well, I'm just pointing out how it's absolute nonsense and it wasn't true. So I made these arguments pointing out how, no, those are field lines. They don't have anything to do with the lines of force Maxwell actually calculated. Maxwell's calculations are about lines of force, not field fucking lines. You should critique physicists. What the fuck is this? He is a physicist, retard. Are you doing no good to anyone with this? You are doing... yeah, fuck you. Who the hell are these turds? Oh, god damn. So no counter argument. Nothing even relevant. Not even close to on the subject. It's just so bad. I mean, you're defenders of science. You're showing... right now, you're showing the future just how bad human beings are. Just how you've lost all integrity because even your intellectuals, even your believers are useless sacks of fucking lying shit. Okay, does this guy even get the point? Does this guy ever get the point? So I don't know why he's saying that. Who knows what that even means? But Jack Nicholson icon he stole, so I just get rid of him for that alone. You're not Jack Nicholson. Anyway, God, humans are just such garbage. Ugh. God, just hate this fucking planet. Fucking scurvy, religious kook everywhere, you know. All these people thinking they have some, I'm grokking reality. Yeah, you're not grokking shit. Yeah, you know, you're squeezing your own shit. Idiots. Fuckatards. Morons. That's all there are.